Right now, over 10,000 active satellites are in low Earth orbit, or LEO, the zone just above Earth's atmosphere, where most commercial satellites reside. Down below on the surface, millions of miles of high-voltage transmission lines connect nearly every aspect of the global economy. In September of 1859, a massive solar flare slammed into Earth, causing telegraph wires to spark and catch fire. That was the Carrington event, and it remains the historical benchmark for a severe geomagnetic storm. If a storm of that magnitude hit today, our modern transmission lines would act like continent-spanning antennas. They would capture the storm's electromagnetic energy and funnel massive currents directly into the vulnerable grounding points of our electrical grid. By covering the planet in interconnected wires and filling our skies with delicate electronics, we have accidentally engineered a planetary-scale target for space weather. When those solar surges, known as geomagnetically induced currents, or GICs, enter extra high-voltage transformers, they disrupt the machine's magnetic core. This causes a phenomenon called half-cycle saturation, where the magnetic flux physically spills out of the core and into the surrounding steel tank walls. As the flux spills out, localized temperatures inside the transformer spike to 300 degrees Celsius in a matter of minutes. This flash boils the internal cooling oil and melts the paper insulation, destroying a massive, custom-built machine that takes years to manufacture and replace. Up in orbit, the threat is physical friction. Solar energy heats Earth's upper atmosphere, causing it to puff outward. This sudden expansion creates immense drag, acting like a brake on low-orbiting satellites and pulling them down toward a fiery re-entry. To defend against this, operators need to know exactly when and where the solar energy will hit. But our current early warning system relies on a point-and-guess method. We fly single, isolated sensors through a massive magnetic field and try to estimate what the rest of the storm is doing. Because we only measure isolated drops in a magnetic ocean, grid operators and satellite companies are effectively blindfolded. Right now, they often have only minutes of warning before a surge strikes. On April 9, 2026, a rocket will lift off from French Guiana, carrying the SMILE mission, the solar-wind Magnetosphere Ionosphere Link Explorer. Its entire purpose is to eliminate that blind spot. Instead of flying through the magnetic field to take a single localized measurement, SMILE will capture a continuous global movie of Earth's entire magnetic shield as it reacts to the sun. To get the whole system in the frame, you have to move the camera way back. SMILE will fly in a highly elliptical orbit, swinging out to 121,000 kilometers away, nearly a third of the distance to the moon. By stepping back to view the whole board, we can finally stop reacting to isolated alarms and track the storm with tactical precision. The primary tool for this is the Soft X-ray Imager, or SXI. It uses highly specialized lobster eye micropore optics, a grid of tiny square tubes mimicking how crustaceans see, to achieve a massive field of view. This imager detects solar wind charge exchange. That is a process where solar particles collide with neutral gas in our exosphere, emitting soft X-rays. By capturing these X-rays, SMILE can actually watch the invisible front edge of our magnetic shield buckle and deform in real time. While the SXI watches the outer shield, a second instrument, the ultraviolet aurora imager, looks down at the poles. It continuously monitors the northern aurora to track exactly where that incoming solar energy is dumping into our atmosphere. When you combine the two, you get a direct link between the outer magnetic compression and the inner atmospheric reaction. This gives operators a precise map showing exactly where and how intense the electrical currents on the ground will be. Because we can see the full chain of events unfold from outer space down to the poles, we can increase our high-certainty warning times from a few stressful minutes to several days. That lead time turns a natural disaster into a solvable logistical problem. It gives power grids the window they need to safely power down and cool their transformers, and it gives satellite operators time to raise their orbits before the atmosphere expands. The SMILE mission represents a rare 50-50 partnership between the European Space Agency and the Chinese Academy of Sciences, built through years of complex diplomatic coordination. To make this work, the hardware had to be entirely free of ITAR, the regulations restricting the export of U.S. defense and space-related technologies. By keeping the mission ITAR-free, European and Chinese engineers were able to collaborate directly, forming a rare technical bridge between the West and Beijing. For China, co-leading this project is a strategic opportunity to act as a provider of global public goods, demonstrating shared scientific value during an era where most countries are strictly separating their technological supply chains. The shared terror of a Carrington-scale storm wiping out trillions of dollars in electrical infrastructure is so severe it forced a practical working alliance across some of the deepest geopolitical divides of the decade. That alliance comes just in time. The 2026 economy is rapidly pushing artificial intelligence into orbit, building massive orbital data centers that rely entirely on stable solar conditions to operate. With our terrestrial power grids and our orbital tech sectors now fully dependent on one another, proving that we can survive a severe solar storm has become the absolute bedrock of global economic stability. By finally illuminating the invisible forces surrounding our planet, humanity has established a unified global shield to protect the electronic heart of our civilization.